Okay, so today we're going to be looking at free radical substitution for A-level chemistry. Now this is a reaction that you would have seen in GCSE chemistry, but in year 12 you need to understand the mechanism, how does the reaction actually happen. Well, we know it uses UV light, and without it it's not going to take place. So what's going on? Well, we have what is called first an initiation step. Okay, that's step one, initiation. Now in this step, the UV light is going to dissociate the chlorine-chlorine diatomic molecules bond. How does that work? Chlorine-chlorine breaks apart to become two chlorine free radicals. One chlorine takes one electron and the other takes the other. That is known as homolytic fission, an equal sharing of the electrons when the bond dissociates. Now note that I've used curly arrows here, and they are half-headed arrows as well. So the half-headed arrow shows us the movement of one electron only. Now don't get me wrong, that species there, the chlorine free radical, has no charge. Okay, the net charge is zero, just like the molecule it came from. Now we know that diatomic chlorine has no charge, so if it's split equally, the 17 protons and 17 electrons on one side, 17 protons, 17 electrons on the other, you're going to end up with 17 protons and 17 electrons, so no net charge. A usual mistake is to think that that dot represents an overall negative charge. It doesn't. It's just an unpaired electron. It makes it extremely reactive because it doesn't have a full, complete outer shell. In fact, normally when we did dot and cross diagrams back in year 10, for instance, you would have drawn the chlorine with 1, 2, 3, 4, 5, 6, 7 electrons. Well, that's the 7th electron there. We just don't draw the others. Now, what happens next? Let's put the UV light in there to remind ourselves of this. So UV light is only used in the initiation step. Once the reaction starts, it'll keep on going to completion. So the second step is propagation. Propagation. How does the reaction continue? Well, the chlorine free radical is going to collide with something. Now, yes, we go straight into the mechanism. It reacts with the methane, but it could collide with anything else in the reaction mixture. It could collide with another chlorine free radical, but one, that would end the reaction, and two, not that many chlorine free radicals are generated in the first place, so it's quite difficult for that to happen. It could collide with another molecule of chlorine, but that wouldn't result in anything different. There'd be no change there. But what if it collides with a molecule of methane, okay, or the particular alkane that you are using in the mixture? Well, let's draw it. Displayed so we can see the electron movement. Try and keep it green to show chlorine. Okay. So, the chlorine free radical collides with the methane molecule, and the outer shell overlaps with the outer shell of the hydrogen. Technically, it's the molecular orbital, but we can talk about that a little bit later if you like. The electron enters the shared space between the hydrogen and the chlorine, and the electron from the hydrogen has the highest probability right now of being found between the carbon and the hydrogen. That probability shifts to becoming highest probability between the hydrogen and the chlorine. What I'm trying to say with that is it doesn't move in the mechanical sense, but for your exam, for the purpose of writing this in an exam, you can say the electron moves. So let's draw that. That line represents a single bond, which is a pair of electrons. So one of them moves into this shared space. This electron moves into that shared space, and this electron here remains on the carbon. Now, one electron and another electron are going to make a single covalent bond. So let's draw the result of this. We have hydrogen, hydrogen, hydrogen. We also have the hydrogen chloride that was just formed. But we also have this electron that is now unpaired. So we have just generated a methyl free radical. And one of the products, hydrogen chloride. What happens to the methyl free radical? Well, it could collide with just about anything, but let's assume that it collides with a chlorine molecule. Let's draw it down here. So this is the second step of the propagation. There we go. Plus chlorine molecule. Right. Well, likewise, the chlorine gets closer and closer and closer, collides with the methyl free radical. This electron moves to the shared space between the carbon and the chlorine. This electron here shifts here, and this one remains on the chlorine. And what we have now is one of the products, which is chloromethane, and we have just regenerated the chlorine free radical. And that's why it's called a propagation reaction. And that's why it only requires a small amount of UV light. UV light generates the chlorine free radicals. Once they're generated, then the reaction can keep on going. So the chlorine free radical appears here, is regenerated, and continues to attack more methane molecules. Now, having said that, a way to check if we have our equations right, okay, one thing we can do is add these two equations together. Now that's not something that they would ask you to do in a test, but just for our own sake, to make sure we have it right, what we can do is add these two equations together and then just cancel out anything that's repeated on each side of the equation. So, if we did that, we would end up with, blue pen for this one, methane plus chlorine gives chloromethane and hydrogen chloride, which shouldn't be any surprise, but that is the reaction that you saw in year 11. Methane plus chlorine gives chloromethane and hydrogen chloride. Of course, the reaction has to end somewhere. It can't just keep on going and going and going forever. So, the third and last part is the termination step. Well, what happens if two free radicals were to collide with each other? Well, one unpaired electron and another unpaired electron are going to make a pair of electrons, which is a covalent bond. So, let me rub this out, and I'll show you the termination steps. Simple way to remember it, by the way, is that step 1 has one reaction, step 2 has two reactions, and step 3 has three reactions. So, 3. Termination. Now, for the initiation, they usually do ask for curly arrow annotation. For propagation, it's hit and miss. Sometimes they do, sometimes they don't. For termination, rarely they ask for the curly arrow annotation, but we'll do it just in case. So, if a chlorine free radical happens to collide with another chlorine free radical, then this electron moves into the shared space, this one does too, and we end up with, well, one of the reagents, which was chlorine. If a methyl free radical was to collide with a chlorine free radical, okay, well, this electron goes here, this one goes here. Please note that I am using the arrow, I'm starting the arrow from the electron. It's the electron that moves. Okay, you should not be drawing things like the arrow coming away from the actual atom. Okay, they will pick up on that. Well, that is going to give us one of our desired products, which is chloromethane. And finally, we have the case where a methyl free radical could collide with another methyl free radical. And the mechanism explains this perfectly. Why do we find trace amounts of ethane in the final reaction mixture? Well, it's because two methyl free radicals, when combined together, form a single bond between themselves and make ethane as one of the trace byproducts. This one they do like to ask quite often in the tests. Now, having said that, some of the questions that they ask after this are things like, state another organic byproduct of this reaction. Okay. Now, chlorine, for instance, is not an organic byproduct. It's not organic, so you can't use chlorine. If they're asking for another organic byproduct, you can't use ethane either. What can you use? Well, sometimes what you can have is multiple substitutions on the same alkane. So I'll give you an example of that right now. If you happen to end up with chloromethane, for instance, CH3 Cl, and that, well, happen to bump into, I say bump into, I mean collides with a chlorine free radical, well, the chlorine free radical will remove one of the hydrogens, leaving CH2 Cl dot plus the hydrogen chloride byproduct, and then this free radical can now collide with another molecule of chlorine to give CH2 Cl2 dichloromethane, and don't forget, let's not forget to regenerate that chlorine free radical. This does typically happen if you use larger quantities of the halogen. So if you use 2 moles of chlorine, your typical product would be dichloromethane. 3 moles, you get trichloromethane, and 4 moles of chlorine, you'll max it out at tetrachloromethane. Okay. So one of your byproducts that you could use is this one, dichloromethane. You could do trichloromethane or even tetrachloromethane. All of them would be suitable for this. I did say that we would look at the quick way of doing it. Right? If they don't ask for curly arrows, then it makes our life a little bit easier. So let me just get rid of this. So I'm going to rush through this one. So we've got initiation. Just use a black pen now, it's a lot quicker. Initiation would be chlorine using UV light to make 2 chlorine free radicals. Propagation would be methane and a chlorine free radical to make the methyl free radical plus one of the products, hydrogen chloride, and the methyl free radical generated here plus chlorine, one of the reagents, will give us our product chloromethane and regenerate the chlorine free radical. And finally, termination. We have 2 types of free radical, and therefore we have 3 potential products. One being the chlorine, the chlorine free radical meets a methyl free radical. We get chloromethane, one of the products. By the way, it's okay to put the dot there for the free radical. Technically it should be on the carbon, but that's not something they're too picky with. And then if we have two methyl free radicals, just checking to see if it fits on the screen there, you get C2H6 ethane. So that's the shorthand form way of doing it without having to use curly arrow annotations. It's a lot quicker, and like I said, typically they ask for the curly arrow annotation for initiation. Sometimes they do, sometimes they don't for propagation. Typically they will do if it's a small alkane that you can draw displayed. If you want to do curly arrow mechanism, that's fine, but sometimes in tests they ask for things like show us the reaction between chlorine and cyclohexane. Now, nobody wants to be drawing the displayed formula for cyclohexane, right? But for methane or ethane, yeah, they could ask for that. And then the bigger the halogen is, so for instance, if it's especially if it's not symmetrical, or things like propane, for instance. Well, propane, you can remove the hydrogen from carbon 1, but you can also remove it from carbon 2, therefore giving a wider range of byproducts. You could get the linear hexane, but then you could also get 2,3-dimethyl butane, or you could get 2-methyl pentane. Have a go at doing it and you'll see those extra byproducts that you can get.